we'll wait just one more minute or so, and then we'll get the ball rolling.
Should I share the screen now?
Yeah, sure.
Can you see it?
Yeah, it looks great. All right. Yeah, I'll go ahead and we'll introduce the speaker, and then people can keep streaming in, and that's fine. So thanks everyone for coming again to our virtual seminar series. This week we're really excited to have Xiaomeng from Jinan University. So Xiaomeng graduated from UC Davis ARE a couple years back, and he's been doing some really interesting work in the environmental and agricultural and applied econometric space. So he's been extremely generous to join us tonight. It's 11 p.m. In China right now, so he's making big sacrifices in sleep in order to share his really interesting work with us. So we're really excited to have him. Just real quick, a reminder on how we handle the questions during the talk, just in case anyone is new. What we've been doing, and I think it's been working pretty well, is to have people, for shorter questions, kind of clarifying questions, or one-sentence questions, to just type it in the Q&A box. And then Alex and I will be monitoring that, and we'll ask the questions on your behalf. If you have kind of a longer or more nuanced thing that you think might require some discussions, if you want to do the hand raise on Zoom, then we'll unmute you, and we'll have some back and forth dialogue. So that's how you get your questions answered. Yeah, with that, just we'll hand it over to Xiaomeng. Thanks so much for being with us.
Thanks, Matt. Well, thanks for the invitation. It's a really great pleasure to virtually be here and to present this work in progress. So today, what I'm going to talk about is growing season adjustment in response to climate change, and this evidence from China. This is joint work with my co-author Wei from China Center for Agricultural Policy at Peking University. And this is still work in progress, so any suggestions, questions, comments are very well appreciated. We all know that climate change has been regarded as one of the most important challenges that we face in this century. And among many of the concerns related to climate change, a key issue is about food and agriculture. If you look at the IPCC report, you will see at the front that there are a lot of discussions on the vulnerability of agriculture to climate change, and how severe climate change constitutes a threat to human beings because it threatens future food security. And over the past 2 decades, there has been a very rapid development in the literature on understanding how climate change, or more precisely, how climatic factors affect crop production. And since the important work by Shenkan and Roberts, it has become very popular to use panel estimation to identify how things like temperature and precipitation affect crop yields using observational data. And we have seen many applications of this type of analysis on US agriculture, on Africa, on China, and on European countries. And for popular crops like corn and soybeans, the general consensus is that the accumulation of moderate heat will be beneficial to yields, but the high temperatures will be really detrimental to yields. And in the context of warming, on aggregate, this will lead to a net loss of crop production, and the loss can be huge. For example, in Shenkan and Roberts, they predict a 40 to 80% loss in corn by the end of this century. So one thing that has not received much attention in all these quantitative, or most of these quantitative studies, is that how we define growing season. Well, the common practice is that we set a time window that encompasses the typical growing season of a crop in a country, and we hold that window fixed in our panel estimation. And this practice is going to lead to two issues. From an empirical perspective, by doing so, we essentially neglect any potential human adaptation on the margin of adjusting growing season. And on the other hand, when it comes to interpreting these results, especially when we try to extrapolate the estimates into future, our yield predictions based on those climate projections will likely overestimate the impact. And this can be mechanical because in a fixed time window, warming pretty much means shifting up temperatures for all days within that window. And the negative impacts associated with those high temperatures will just be magnified. But in reality, there has been anecdotal evidence that farmers do adjust growing seasons according to observed changes in their local climate. And there's also a group of phenological studies that use observational data to see if timing of crop production is related to climate conditions. And not surprisingly, they found that there's a cross-sectional association between warming and the timing of production. And they argue that this is an indication that climate change will also lead to a change in the timing of crop production, like the planting time. In the economics literature, some of Ariel's earlier work has pointed out that growing season adjustment can be a very effective way of adaptation to climate change. In one paper he wrote with Richard Just, they used simulations to show that after changing planting date in an optimized way, the negative impacts of warming can be substantially mitigated. As in this table, I copy-paste from their paper, in these major corn states in the US, the mitigation effect can be around 35 to 70%. And this pretty much is going to offset the predicted loss in Sri Lankan rubbers. That's about 40 to 80%, as I mentioned earlier. So we know that the empirical literature has sort of overlooked potential adjustment in growing seasons. We think there could be adjustment in reality based on anecdotal evidence and based on phenological studies. We also see simulations and calculations that growing season adjustment can matter a lot. The missing piece here is really that we don't have very solid empirical evidence on how growing seasons actually adjust in response to temperature and precipitation. And part of the reason could just be data limitations. So what we want to do here in this research is to see if we can empirically confirm that climatic factors like temperatures and precipitation induce behavioral response in growing season adjustment. And we're going to conduct rigorous econometric analysis with detailed macro level observational data. And based on our quantitative estimates, we will further discuss what's the implication of our findings and how does it fit into the big picture of climate change impacts on agriculture. So just to first give you a preview of the results, this is essentially an empirical paper. The data we use come from a novel data set that contains detailed crop progress information collected at specific locations in different parts of China. These locations are in a network called agroclimatic monitoring system that I will introduce in more details shortly. In this analysis, we focus on corn specifically, and by combining these macro level crop progress data with station-based weather information in a panel estimation framework, we identify the effects of temperature and precipitation on two specific margins of corn's growing season adjustment. One margin is the planting date. The other margin is the length of growing season. And the main finding here is that receiving higher temperature and more precipitation before the normal planting time will in general advance the planting date. And having higher temperature and more precipitation after the crop being planted will shorten the length of the growing season. And these estimates are essentially short-run adjustment. We also explore potential long-run adjustment with alternative estimation strategies. But in our analysis, we do not find evidence of long-run adjustment on top of the short-run adjustment. But the short-run effects we identified are significant both in statistical sense and in terms of their economic meanings. If we refer to the median site in our sample, based on climate projections by the end of this century, climate change is going to induce about 2 to 6 day earlier planting date. And also for growing season, the length of the growing season is going to be roughly 8 to 16 days shorter growing season. And combining these two margins, it means that the ending time of this median site, the ending time of the growing season at this median site will be shifted forward by about 10 to 20 days. Based on previous literature on warming impacts on crop yields, on average, this shift in growing season can help corn to avoid more than 15% of the loss caused by high temperatures. And this calculation is just based on the short-run response we identified in our estimates, not including other potential long-run effects that we are not able to capture in our estimates. Besides, we also find some regional heterogeneity across different agricultural regions in China. In terms of the contribution of this paper, as far as we know, this is the first rigorous econometric estimate of temperature and precipitation effects on growing season adjustments. And our findings here contribute to our understanding of climate change impacts on agriculture, especially for better understanding the impacts on crop production, building on those yield estimates we already have in the literature. In terms of the country context, since we use data from China, we also make a contribution to extending our knowledge on climate change impacts on Chinese agriculture. And this is important because on one hand, agriculture is very big in this country and is feeding a large number of population. And on the other hand, what we know about climate change impacts on agriculture in this country is still fairly limited. The empirical estimates we got in this paper sort of echoes those simulations in Ortiz-Bobia and Just, and this brings a reassessment on predicting yield loss and their future climate, which could have very important policy implications. And from the perspective of explicitly measuring a behavioral response to changes in climatic factors, we also build on this emerging literature on understanding agricultural adaptation to climate change. We have seen early work on crop switching, and some of my own work have discussed cropping pattern changes and harvesting decision adjustment. And there are also some of the recent work examining input adjustments. The paper we will talk about today builds on all these discussions by looking at a different adaptive margin.
Xiaomeng, we've got a question real fast from Jinhua Zhou, which says, agronomically, why do earlier planting and shorter growing seasons lead to higher yields?
Oh, I see. So earlier planting day and shorter growing season by themselves, they do not lead to higher yields. So the yield calculation here is really because the move or the shift of the growing season can help those crops to avoid some of the high temperatures that will be realized in the growing season if the growing season does not change the time. I'll talk in more details when we get to the details. And if that still doesn't make sense, just let me know.
Thanks.
So as I mentioned earlier, this is an empirical paper, and part of the reason that we are able to empirically answer our research questions because of the novel data sets that we have. So let me first introduce the data we use in some more details. The main source of crop data we use is a site-specific crop progress information. The data were collected by the National Meteorological Information Center of China and stored in their data archive. The data is not publicly available, and we are able to use this data under a contract with the center. There are nearly 800 sites in this data network, And the years we have are from 1993 to 2013. So in total, we have 21 years. The information we have in this data includes exact planting and maturity dates specific to site, crop, and year. And these sites are selected in a way that they're representative of the agricultural production in that region. And the fields are still planted and managed by ordinary farmers based on their own decision-making. So the network system is purely for monitoring crop conditions on these sites. In this paper, we decide to focus on corn specifically. We have few reasons here. First, it's an important annual crop in China, and China is the second largest corn producer in the world behind the United States. And second, is a crop that has been shown to be sensitive to climate change, especially for the sharp nonlinearity in corn's yield response to temperature that has been widely documented in the literature. So focusing on corn is highly relevant. And also, I will show you in about 2 more slides. Over the past few decades, we have seen some warming trends in corn producing regions in China, and this makes our discussion even more relevant.
So there's a few questions in the chat, Xiaomeng, that I think now is probably a good time to address. So first there's a question from Hong Li, and she asks, why will growing season become shorter given earlier planting dates? So you might think intuitively that earlier planting dates in northern regions would lead to longer growing seasons.
Right. So here, so there are 2 things. So in terms of empirical estimation, we actually estimate planting date response and the length of growing season separately. And in terms of projecting in the future, because the warming, so sort of the warming under the climate projection can be very large, so that even if we have shifted forward the planting date, those heat that's useful for crop growth accumulated within the growing season can still be realized in a shorter time period, so that we can have both moving forward of the planting date and the shortening of the growing season in the same time. So there's another question.
Yes, so this is a follow-up to an earlier question. My Wish asks, so isn't the impact coming from genetic improvement in the form of shorter duration varieties that allow farmers to harvest the crop earlier, related to why earlier planting agronomically would offset some of this damage?
So yeah, so here, I guess like technically speaking, what we are estimating here is sort of independent from this genetic improvement. So of course, there are those genetic improvements play a very important role in terms of shortening the duration of the growing season. But here, the estimates we're getting is based on purely the effects of temperature and precipitation, and sort of independent from that channel. Yeah.
Great, thank you.
So here, so I'll talk about weather data. The weather information we will use here comes from the network of nationally certified weather stations. The source of the data is from China Meteorological Data Service Center, and the data we obtained have observations in roughly 700 weather stations, so all over China from 1981 to 2015. And at each station, we have information on daily maximum and minimum temperatures and also precipitation. Some of the agricultural sites are co-located or very close to those weather stations, but many of them are not. So the way we match the 2 data sets is that we interpolate weather station information to the location of those agricultural sites. The specific method we use is an inverse distance weighting within the radius of 200 kilometers. This is also the strategy that has been adopted in previous research using the same source of weather data in China. And they have shown that this strategy is fairly robust. And in addition, for the analysis on regional heterogeneity, we supplement geographical data on the classification of agricultural regions or agricultural zones. The classification is made by a multi-departmental expert team based on factors on environmental endowments that are directly related to agricultural production.
So there's another question in the chat. So this is from Scott Swinton, and he asks, does the growing season effect mean that corn needs a given number of growing degree days, and warmer weather can allow accumulating those by an earlier date?
Yeah, that's the idea. But here we didn't really calculate the specific number of growing degree days that's required. So in estimates sort of reviewed outcome that we see under a warmer temperature, the actual growing season length is shortened. But the intuition is really that the sufficient amount of heat has been met in a slightly shorter time window, so that the growing season length is shortened. That's the idea.
Great, thank you.
So just to give you a better sense on the spatial distribution of our data points, here I'm plotting a map with the locations of our raw data. All the round circles here are locations of agricultural sites, and those circles with red color are sites that we observe corn planting. The density or distribution of these sites follow the relative importance of agricultural production in that region. So for those places you don't see many circles, those are places with relatively few agricultural activities and small number of populations. Mostly are remote regions and mountainous regions. And those small crosses, those are locations of weather stations. You can see that some of them are co-located or very close to those small circles, but many are not. By doing the inverse distance weighting for a circle, we essentially use weather at those crosses near that circle. And the closer is the cross, the more information we rely on from that cross. If a cross is at exactly the same location with a circle, then the circle only uses weather information at that co-located cross, because the weight of that cross in this weighting strategy will become 1. And different background colors indicate the different agricultural regions I just mentioned. There are in total 7 different regions. And the vast majority of our corn observations are within 5 out of the 7 regions. And these regions are the Northeast, the Northwest, and this is called the Huanghuaihai region. Is actually a region with 3 famous rivers named the Huang River, Huai River, and Hai River. And for simplicity, we can just call it Triple H. And the other one is this is Southwest. And for the rest, these 2 regions, we combine those 2. This one is the Yangtze River Delta, and this one is called South, because we only have very few corn sites there, so we combine those 2. So in the end, we have 5 regions with corn observations. And just to give you a sense on how the national corn production is distributed or divided spatially, this is a map I got from USDA FAS. It shows that the Northeast is the most important corn producing region. Following that is part of the Northwest and the Triple H, then the Southwest, and the least important is the Yangtze River Delta, and that's also the major region for rice planting. On this slide, we show the observed temperature trends in our data for the 5 agricultural regions where we observe corn information. In each panel, we show a kernel density plot of the trend coefficient in site-specific annual temperature. These coefficients are obtained by regressing annual temperature level on a site-specific slope of time using temperature data from 1981 to 2015. And on the horizontal axis is the slope coefficients in the units of degrees per year. So for example, the positive 0.2 means that the trend indicates a plus 0.2 degrees Celsius per year, or equivalently plus 2 degrees Celsius per decade. So that would be very large trend of warming. What these plots are telling us is that it seems there has been some warming trends in these corn regions, and these trends will continue when we later see climate projections. If we think these trends are indication of the local temperature distribution moving toward a higher level, it means that we will likely see more high temperatures that are detrimental to yields. In this context, it's relevant that if we can find evidence of growing season adjustment and the potential to avoid some of the high temperatures by simply shifting the growing seasons. Now let's turn to estimation. As I said, we will look at two margins. One is planting date, the other is the length of growing season. Here we will first look at planting date. We will use a standard panel fixed effects estimation. The cross-sectional units are agricultural sites labeled by I. The time dimension is here, labeled by T. The dependent variable PD represents the planting date of corn at site I in year T. And there's no double cropping for corn, so there's only one corn growing season for any site in a year. The variable PD is simply the number of days since the first day of a calendar year. So a smaller number means an earlier planting date. The use of weather variables here is slightly complicated. Let's focus on temperature variable first. So here we wish to be flexible in modeling how planting days respond to temperature over different weeks. So for each site I in each year T, we will have a set of weekly average temperatures. And the weeks we consider are weeks before the normal planting date of a site. So in our notation, in the subscript of T, we have this I'm I minus J. I'm I represents the median planting date of site I of all years. And the minus J is just the Jth week prior to that median planting date. So in practice, we're going to include 12 weeks for tracing the temperature effects over different weeks before the normal planting date. And one thing to note is that here the median planting date is specific to the agricultural site. And in reality, and also in our data, the median planting dates are different at different locations. And we show the distribution of these median planting dates in this figure. And this means that although we are tracing backward for 12 weeks for all sites, those weeks are not the same weeks for different sites. If site A's normal planting date is April 1st, then its 12-week time window will be in January, February, and March. But if site B's normal planting date is on May 1st, then site B's 12-week period will be in February, March, and April. But within the same site, the 12-week time window is always the same for every year. Another thing to note is that for each site, we use median planting date instead of year-specific actual planting date. If we use year-specific actual planting date, the 12-week time window for the same site will be changing over time. And in this case, it's going to become endogenous to weather realized in that year. So this is certainly something we don't want to have when we try to estimate the behavioral change in planting date. Yeah.
Is now an okay time for questions? Or
yeah.
Okay. All right. So so Felicia has a question related to the trends. So you showed trends for temperature, but how has precipitation changed in each of these regions over time? And she writes, I would imagine it's quite different for, not gonna nail this pronunciation. Yilongjiang in Jilin versus HHH versus Xiangjiang. And that would affect farm growing season.
So it's like for different agricultural regions I mentioned, the patterns will be different. Oh, that's a really good question. I can't remember if I have done this. So I don't really have a good answer at this moment. But later on, when it comes to climate projections, actually in the projections, we don't see a systematic change in terms of precipitation patterns, even if we break down into different agricultural regions. But yeah, I'll go back and check in the observed data, what's the pattern of precipitation change in different regions? That's a very good question.
And then I have a question related to this 12-week window.
Mm-hmm.
So I guess I'm not understanding intuitively why you start small j at 0 instead of a negative number, because it looks like you're kind of only testing for effects on the people who plant before the median harvest date. But you might think that there could be changes that affect how people who always plant after the median harvest date, how does weather affect them? And that seems like it's not really captured since you're starting the small j at 0.
So you're saying that I should have like -1 or something like that?
Yeah, or -6 or however, just to capture the full distribution of when people are planting.
Oh, I see. Yeah, maybe we can try this. I think when we're doing this, the idea is really to just capture, because the rationale or the thought process that we think farmers may observe weather before their normal planting time. And if they decide to advance their planting date compared to what they do in normal case, that has to be they observe, say, warmer temperature before the normal planting time. So that was our thought process. I need to think more carefully if we also include some weeks after the median planting days. What's the variation will be. I need to think more carefully about that, but that's a good point. I'll think about that.
Great, thank you.
So here, as I mentioned, the reason for all these complications in this estimation design is that we wish to see how those weather deviation in a year right before the size normal planting time is going to induce changes in actual planting time of that year. So we define variable in this fashion. And for our precipitation variables, these precipitation variables are weekly cumulative precipitations, and they are defined exactly as how we define weekly temperatures. And for the rest of the terms, the HRT is a provincial level quadratic time trend. And this is for picking up background trends that related to things like technological change. And alpha I is just the fixed effects for agricultural sites. And for statistical inference, we cluster our standard errors by agricultural sites and by province by year pairs, so that we allow for arbitrary correlation in the error structure within the same site over years and across nearby sites within the same year. Now let's look at the results. So this slide shows the temperature coefficients we estimated from the regression on last slide. The dots are point estimates, and the bars are 95 confidence intervals. These are effects on planting date if the weekly temperature becomes 1 degree higher. And there are 12 estimates because we have traced back for 12 weeks. The week on the left is closer to the normal planting date, and the week on the right is farther away or earlier from the normal planting date. And from the pattern, we see that the largest impact occurs around 1 month before the normal planting time. And then for the third and fourth week, a 1 degree increase in that week's average temperature is associated with an earlier planting date of roughly 0.25 days. As the time becomes earlier and farther away from the normal planting date, the effect of higher temperature becomes smaller and closer to 0. And the next slide plots the precipitation coefficient in the same fashion. Notice that the scale of the y-axis is different because here the unit of precipitation is centimeters. So the magnitudes are not really directly comparable with the last figure. But if we just look at the patterns of the coefficients, it seems that the largest effect also occurs in between like 1 to 2 months before the normal planting time. But the estimates here are only marginally significant. So one of the advantages of doing this flexible estimation is that we are able to sort of approximate these temperature and precipitation effects as a non-parametric function of time. But the downside is that when the correlation in weather between neighboring weeks are high, and the effects are not that different across weeks, then we will lose a lot of precision in estimating the coefficient. So for getting more precise estimates and also for easier interpretation of the results, we're going to revise the regression here by combining every 4 weeks within the 12-week window, so that we eventually will only have 3 temperature coefficients and 3 precipitation coefficients. And the rest of the setup and the underlying identification assumption are still unchanged. And we call this as the baseline estimation. So through the subscripts, you can see that we have the 1st to the 4th week, the 5th to the 8th week, and the 9th to the 12th week at 3 4-week periods. And in this table, we present these baseline estimates. So the 6 coefficients are temperature and precipitation effects for every 4 weeks within the 12-week period before the normal planting time. For example, the first estimate represents the effect of increasing 1 degree in average temperature of the 4-week period right before the normal planting date. And this effect is about negative 0.75. This number is roughly equal to adding up the first 4 weekly temperature estimates in our earlier flexible regression. So the 3 temperature estimates are in general both qualitatively and quantitatively consistent with our earlier weekly estimates. This is not surprising. And the impact is larger when it is closer to the normal planting time. And another way to sort of contextualize general effects on these estimates, suppose the pre-planting temperature uniformly warms up by 1 degree. Then the planting date will be advanced by roughly 1.2 days. So I'm simply adding up the 2 significant temperature coefficients. For the precipitation effects in this baseline specification, we find that the effect is only significant during the second 4-week period. And in terms of the magnitude, a 1 centimeter increase in weekly accumulated precipitation during this period will induce about 1.2 day earlier planting time. And the precipitation compared to the temperature effects is generally weaker in terms of statistical significance. Now let's turn to the second margin, the length of growing season. Again, we first use a flexible specification that approximates temperature and precipitation effects as a non-parametric function of time. The dependent variable, GS here, is the length of growing season. And because in our data, we do not have information on actual harvesting time, we only have information on the date of crop maturity. So here, the length is defined as the number of days between the planting date and the maturity date. In this estimation, the weather realization we care about is during the period that crop has been planted and is growing. So here, our weekly temperature and precipitation are weekly realizations after the planting time. There's one more distinction between this length regression and the earlier planting date regression. Here, we use year-specific actual planting date instead of the median planting date when defining the relevant time period. The rationale is that in the case of planting date adjustment, the response is more behavioral. So we need to fix the time window at the given site to avoid the endogeneity problem I described to you. In the case of growing season length, the response is more biophysical. So the way temperature and precipitation affect growing season length, we believe is through meeting the heat and water demand for crop growth. And so this is, in some sense, conditional on the actual planting date.
One question, Xiaomeng.
Yeah.
So this comes from Scott. So he asks, how was maturity date defined? And he writes that he hopes it's not a function of temperature itself, because then it would seem endogenous.
Yeah, that's a really good question, and it's very important. So for these monitoring system, they actually have a very long manual or protocol in terms of how they define different days. And for each specific crop, they actually have a more than 60-page book with very detailed conduct and guidance on based on agronomy knowledge, how they define, say, maturity. And this definition of maturity date is based on experts' on-site observation of the crop, and they follow a very detailed protocol to define the date that a crop is considered as matured. So it's not based on calculation of growing period days. It's simply based on observing the crop.
And then another question from Felicia. She asks, does a faster maturing time pose unusual demands on soil, for example, for nutrients as well? And if so, has this meant the need for more agricultural input, such as fertilizer?
Well, that's a very good question. Well, to be perfectly honest, I don't know. I think it makes sense that I think it depends on sort of the soil nutrition condition in a specific location. But there could be a potential that by shortening the growing season, they actually put extra pressure on the soil nutrients. Unfortunately, we don't have any input use data directly related to those agricultural sites. So I'm afraid we are not able to explore this specific channel of effect, but I think it's potentially very important. Yeah, thanks for the question.
Thank you.
So we were talking about the growing season. So I was talking about the distinction between the length regression and the planting date regression. So here, if you look at the subscript in our T and P variables, here I use this DIT. So it's the actual planting date, specific to site I in year T. And so this is time varying for the same site. And the plus K is simply the K week after this actual planting date. So we determine the number of weeks to be included by referring to the minimum growing season length we observed in our data, and which happens to be slightly less than 90 days, so roughly 12 weeks as well. So here we also include 12 weeks for tracing out the effect over time. And the setup for fixed effects, provincial trends, and also the clustering of the standard errors are all in the same way as we have done in our planting date regression. So turning to the results, first look at the temperature coefficients. As before, the dots are point estimates and the bars are 95% confidence intervals. From left to right is from the week immediately after the planting towards the later course of the growing season. And the pattern of the coefficient suggests that higher temperature in the early part of the growing season significantly reduce the length of the growing season. And the effect sort of diminish as we move toward the end of the growing season. And let's just pick up on a couple of coefficients to interpret. So if we, for example, if we look at the third week after planting, a 1 degree higher in the weekly temperature is going to be associated with about a half-day shortened growing season. And these effects are more or less similar in the neighboring weeks. On the next slides, the precipitation effects are noisier compared to the temperature effects. But we also see this pattern that the effect seems to be larger in the early course of the growing season and becomes very close to zero towards the end of the growing season. And again, for more precise estimates and for easier interpretation of the results, we're going to set the baseline estimation as the one that we group every 4 weeks. So for temperature and precipitation, we're going to have separate coefficients for the first 4 weeks after actual planting, the second 4 weeks, and the third 4 weeks. And all the other controls and the clustering of standard errors are still the same. I'm going to present these baseline estimates of growing season length response in the table. This table shows that, so for a 1 degree higher, in the first 4 weeks, average temperature, that's going to induce a 1.6 days shorter growing season. And the 1 degree higher in the second 4 weeks periods, average temperature is going to induce a about 1.2 days shorter growing season. The effect in the third 4 week period is relatively smaller. For a 1 degree increase, the duration reduction effect is about a half day. And all these effects are highly significant statistically speaking. And the rationale is really that the temperature, because temperature becomes higher, so that the heat that's necessary for crop growth has been met in a relatively shorter time window. And for precipitation effects, we find statistically significant impact in the first and the second 4 week periods. So for 1 centimeter more precipitation in weekly cumulative precipitation, it's going to lead to roughly 1 day shorter growing season if the increase is in the first 4 week. And if in the second 4 week, the effect is about a half day. So until now, what I showed you are the two sets of estimates, one about planting date, the other about growing season length. These estimates are essentially short-run estimates because empirically we rely on year-to-year fluctuation in weather to identify these effects. But if you look at the literature on environmental adaptation or just the adjustment to environmental shocks, we know that the adjustment is normally not immediate. And it's more like a process. It's going to involve recognition of the change. It's going to incur a non-marginal cost to make adjustment, and it also takes time. So the figure I show here is just come from the paper by Kelly, Kostad, and Michel, 2005. It sort of illustrate this idea. So in this sense, the short-run estimates I show you, they cannot capture potential adaptation or adjustment that only be reviewed in the longer run. This short-run and long-run distinction is especially relevant for understanding the adjustment on planting dates. As I sort of mentioned earlier, the underlying mechanism for adjusting planting date and adjusting growing season length are slightly different. The planting date adjustment is more behavioral in the sense that in reality involves farmers' expectation on climate. And this expectation can partly formed by observing the realized weather in the past few weeks, but could also be partly formed by observing the realized weather in the past few years. But in contrast, the adjustment in growing season length is more mechanical in the sense that a farmer just counts, it's not farmer just counts, it's the crop just counts the heat and water received after the crop has been actually planted. So another way to interpret is that just the adjustment in growing season length is conditional on the adjustment in planting date. So in what follows, we want to explore potential long-run effects on top of the short-run effects we have identified. And because of the rationale I just described to you for understanding of the long-run effects, we will only focus on planting date. And empirically, we are going to revise our baseline estimation on planting date in 2 ways, so that we have 2 different approaches to explore this potential long-run effect. The first one I presented here is to incorporate historical rolling averages in the baseline estimation. So in this regression equation, we write temperature and precipitation variables in vectors. And the TIT beta and the PIT gamma are exactly the same specification as in our baseline. So there are going to be 3 temperature variables, 3 precipitation variables, characterizing the current year temperature and precipitation realization in the first, the second, and the third 4-week periods before the normal planting date of the actual agricultural site. The new variables will be the T tilde and the P tilde. Those are still measures of temperature and precipitation realizations in the first, the second, and third 4-week period before the normal planting time, but they are not the realizations of current year. They are averages of the past 5 years realization in the corresponding weeks. The idea here is that the 5-year average is a proxy for the local climate, or sort of the proxy for longer run understanding of the local climate. And because we are using this panel fixed effects estimation framework, the identifying variation really comes from the temporal variation within an agricultural site. So for those T tilde and P tilde, we're using those smooth changes in the moving averages over time. And this is going to be an approximation of variation in local climate. And in the same time, we will still have those variation in year-to-year change in the current weather realization. And those will be the within variation in T and P. So in this sense, T and P will capture short-run response, and T tilde and P tilde will capture long-run response. We present estimation results in this table. For illustration purpose, we put short-run estimates and long-run estimate in parallel in 2 columns, but they're not from separate regressions. All the 12 coefficients on this slide are obtained from a single regression. And the regression contains both T and P and T tilde and P tilde in the same time. And you can see from the results that the short-run estimates are similar to our baseline, but none of the long-run estimates are significant. So in the brackets are the standard errors, and you can see the long-run estimate standard errors are quite large. And we use the same specification, but we change the 5-year average to a version of 10-year average. And we still find very similar results. The long-run estimates are still statistically insignificant. And as I mentioned, we use 2 approaches to explore this potential long-run effect. The second method is the long difference approach developed in Burke and Emmerich 2016. And the basic idea of this, the long difference, is that we will take 2 snapshots of the panel data, one on the beginning year, the other on the ending year, and we're going to form a 5-year average at both ends of the data, and we only use these information so that the transformed data is going to be a panel with only 2 periods, and then we are going to difference the 2 periods, or equivalently, you can treat this as a panel fixed effects estimation with only 2 periods of observations. And the idea is that this long difference approach is gonna, so if the long run change, if there is long run change or response, then we would be able to see it had we allowed for a long enough time gap in our panel estimation. So in the specification, we will only have 1 set of temperature and precipitation variables, and the coefficients associated with these variables are going to be interpreted as long-run effect. And in this table, we present 2 sets of results using the long difference approach. One is to form the snapshots by using 5-year average. The other is to form the snapshot by using 10-year average. But in both cases, we do not find any significant results. So in both cases, in both the moving average specification and the long difference approach, we do not find evidence of long-run adjustment in the planting date. But we wish to be very careful in terms of how we interpret these insignificant results. One thing we wish to acknowledge here is that both the moving average and the long difference approach are actually very demanding on the data variation. So especially if we consider that we have a panel that only spans over 21 years, So the observed change in those long averages could just be too small. And those could be too small to let us empirically identify the effect. So although we don't find evidence of long-run effects based on our estimates, we cannot really fully rule out the possibility that long-run effects actually exist. And intuitively speaking, if we go back to the Kelly-Cost that Michel figured, we would conjecture that the short-run effect we are able to identify is going to be a lower bound estimate, because we would think farmers will be more flexible in adjusting planting date if there is meaningful long-run adaptation.
Can I ask a question, Xiaomeng?
Yeah.
So one thing that I think that might help you get more power here is those tilde variables. So for the short run, it makes perfect sense to me to have just hyper-focused on the planting period. But for these tilde variables, is there a reason that you don't think about kind of past weather during the whole growing season? I might have a belief about kind of what's coming, and then I might think that my planting date is going to adjust to that. So I might think, June's been really warm these past few years. I'm going to plant a little earlier in response to that.
Yeah, that's a good point. I haven't thought in that way, but I think, yeah, there's potential that by sort of observing the weather over the past entire growing season, that's going to change my planting decision. Yeah, I think there's potential that farmers behave in this way. So yeah, maybe we can try incorporating those information in this sort of long run impact estimation. Yeah.
And then I think if you included it as like one big average, that would also help with the power issue, because it's tough when these, it's just.
Yeah, absolutely.
Okay, thanks.
So in what follows, we would like to show you some simulation results that's going to help us to contextualize our empirical estimates. And specifically, we would like to argue that even without additional long-run adjustment or adaptation, those short-run adjustments we empirically identified by themselves will constitute meaningful adaptation in the long run. So the specific data exercise we're going to do here is that we're going to combine our baseline estimates on planting date and growing season length with projected climate by the end of this century under different climate models and different warming scenarios. We'll consider 5 different climate models. Those models have been recently used in the scientific community to evaluate climate change in China. And for each climate model, we consider 2 scenarios. One is RCP 4.5, the other is RCP 8.5. So RCP are representative concentration pathways. A simple way to interpret them are just, so they're just describing different levels of warming. So the RCP 4.5 is sort of the low to intermediate level, and the RCP 8.5 is the high level, or sometimes called the business as usual. And these 2 RCPs are frequently used as benchmark in evaluating predicted outcomes under different climate change scenarios. So we're going to use 30-year average from 2070 to 2099 to represent future climate. And we use a 30-year average from 1984 to 2013 to represent current climate. We choose the year 2013 because that's the year, this is the last year in our sample for the empirical analysis. So the climate projection data is at the monthly level. So we calculate the projected change in climate by differencing the future climate and current climate at the monthly level. And by doing this, we sort of preserve some of the temperature and precipitation variation within a year. And on this slide, we present the calculated difference between future climate and current climate. You see 10 panels here. The 5 on the top are temperature change, 5 on the bottom are precipitation change. Each column is for a specific climate model. We have 5 different climate models. And within each panel, we have 2 kernel density plots. The plot in red is going to represent the calculation based on RCP 4.5, the lower warming scenario. And the plot in blue or green represent the calculation based on RCP 8.5. That's the higher warming scenario. And those kernel density plots are obtained by summarizing the site-specific changes. So we calculate those projected climate change at the level of agricultural sites in our sample. And from the figures, you'll find that there will be systematic warming under all of the climate models, but there's no systematic change in precipitation patterns. For the kernel density plots of temperature change, within each panel, you see the blue or green one is on the right of the red one, and this is expected because the green one is the temperature change under a higher warming scenario. And those projected changes in climate are in general quantitatively different, but in general qualitatively similar. And remember that we would like to do simulations by combining our baseline estimates with the projected future climate. Our baseline estimates are estimates of specific weeks, but the projection is on the monthly level. So what we do here is we first add the monthly difference between the future and current climate back to the daily data of our current climate, of our observations. So we can recover a constructed data on future climate with daily values of temperature and precipitation. And then we multiply our empirical estimates from the baseline with the projected change in climate in the corresponding weeks. Then for each agricultural site, we can simulate the projected change in planting date and growing season and their future climate. And so from another perspective, this is essentially a back of the envelope calculation for each agricultural site. So on this slide, we plot our simulated results using a set of box plots so that we can show the distribution of the simulated outcomes across different sites. So you can see two big panels here. On the left is the results under RCP 4.5. On the right is results under RCP 8.5. Within each panel, we have 5 sets of results. Each set is based on a specific climate model. Within each set, you see 2 box plots. The one in red is for the simulated change in planting date, and the one in green or blue is for the simulated change in growing season length. So the way you read the box plot is that the horizontal line within the box region, those are the median effect or the outcome evaluated at the median site. And the upper and lower boundary of the box region are the quartiles. And those dots further away, those are considered outliers, and they're outside 1.5 times of the interquartile range. And there are a few observations from these plots. In terms of the general patterns, the first, under projected change in climate, most planting days will be advanced and most growing seasons will be shortened. And comparing between these two margins, the effect is generally larger on the length of growing season. In terms of the magnitude, let me just describe those the biggest changes here, the 3 models under RCP 8.5. For the median site, the projected change in climate are going to induce more than 5 days earlier planting date. On top of that, the growing season will also be shortened by more than 15 days. And if we consider the ending time of the growing season, then we combine these 2 margins, it's going to lead to a more than 20 days earlier ending time of the growing season. Of course, these numbers will be different if you look at other climate models or RCP 4.5. So one thing we wish to clarify here is that our purpose of this data exercise is not for getting accurate prediction in terms of the number of days that growing season will shift. And we know that there is huge uncertainty both in terms of climate models and for other potential long-run behavioral change that could happen in reality. Our purpose here is really about to contextualize and to give a sense on the magnitude and the meaningfulness of these induced adjustments. And to move forward one more step, we try to link these induced adjustments in growing season with implication on crop production. in the literature on measuring climate change impacts on agriculture, on crop production, the concept, as Scott has mentioned, is the degree days. And degree days is just a matter of heat accumulation. And especially when measuring accumulation of very high temperatures, we normally use the concept called heat degree days or extreme degree days. Those are accumulation of very high temperatures. And for corn, the heat accumulated above, say, 29 or 30 degrees is usually considered very detrimental to corn yields. So what we do here is that we simulate the heat degree days above 30 degrees in two scenarios. One scenario is that for each agricultural site, we fix the growing season at the median planting date and the median maturity date in our observation. And we simulate the heat degree days each site will have by the end of this century, based on those climate model projections. And the other scenario is that we allow for growing season adjustment based on what we have estimated from our regressions. And remember, for each site, we have simulated the adjusted growing season by the end of this century. So based on that, we can recalculate the heat degree days within those adjusted growing seasons. And by comparing the heat degree days across the two scenarios, we get a sense on how much of the detrimental heat can be avoided through induced adjustment in growing season. And in this table, we present the results. The first four columns are results under RCP 4.5. The rest, the four columns are under RCP 8.5. In each row is a set of results under a specific climate model. Column 1 presents the mean value of heat degree days by the end of the century when allowing for induced adjustment in growing season. In column 2, those are mean values of heat degree days under the fixed growing season. And for columns 1 and 2, in the parentheses are standard deviations. Column 3 is just the difference between the first two columns, and in brackets are the standard errors of a simple t-test. For the fourth column, we translate those differences into ratios. So that's going to indicate how much heat degree days can be mitigated or avoided by simply allowing for those induced adjustment in growing season. So under RCP 4.5, the avoidance of detrimental heat is on average about 6 to 9%. Under RCP 8.5, the avoidance is also higher, on average between 9 to 17%. So when the warming impact is larger, the potential avoidance through adjusting growing season is also larger. And if you're familiar with those yield response model in the literature, the negative effects of yield is typically assumed to be linear in heat degree days. This means that the ratios we simulate here can be directly translated into the mitigation of yield damages. So if you avoid 1% of the heat degree days, you will avoid 1% of the yield loss associated with extreme heat. This is under the assumption that in those yield response models, the yield reduction effect is linear in heat degree days. And here we also wish to emphasize that the induced adjustment in growing season we present here or we use here are all based on our short-run estimates. And there's some reason to believe that those short-run estimates are still quite conservative. So the takeaway from this slide, and this may also be the takeaway of the entire paper, is that if we ignore those induced adjustment in growing season through the margin of planting date and through the margin of growing season length, we will substantially overestimate the negative impacts of temperature, of high temperature on corn yields.
Xiaomeng, we've got a question here from Jinhua Zhou. Let me see if I can unmute him.
Yeah, so I think I'm muted.
Great.
Yeah, okay. So Xiaomeng, this is really interesting. I have a question on this slide. So, I mean, the idea here is that, you know, the yield is going to depend upon this really bad hot days that you're going to avoid. So given that, if I'm a farmer, I would have incentive to adjust my planting dates, not only based upon the temperature before the planting date, but also based upon my anticipation of, the degree days or the hot weather later after planting, right, during the growing season. So when you look at the long run impacts in your regression, that would mean that my planting date adjustment would depend not only on the the several weeks before the planting date, the previous 5-year or 10-year long run averages of the temperature up to 4 weeks before my planting date, but also maybe some kind of temperature after the planting date averaged over the last 5 or 10 years. That might also play a role, right?
Yeah.
Yeah.
Yeah, I think this is also related to Matt's earlier comments. So we didn't think about this channel, but through your description, I think it makes sense. So in the long run estimation, yeah, we probably should consider in some way incorporate those information. I think that makes sense. Yeah.
Mm-hmm. Okay, thanks.
Yeah, thanks. So for the last part of the analysis is about regional heterogeneity in the growing season adjustment. I've shown you this map when introducing the data. The entire China can be categorized into different agricultural zones based on different environmental endowments that are related to agricultural production. So we think because of these differences, those induced adjustment in growing seasons could also be slightly different across different regions. So based on our baseline estimation of planting days and growing season lengths, we are going to further allow for heterogeneous coefficients across agricultural regions. And remember that we have 5 regions with corn planted. So essentially we get 5 sets of temperature and precipitation coefficient. So in this table, we first present results on planting days. So one thing to clarify is that here we put each region in a separate column. This is just for illustration purpose. All these estimates are obtained from a single regression. And for the 5 regions from left to right, it's roughly from the cooler northern China to the milder southern China. And we only see significant temperature effects in the northern region, not in the southern region. And this sort of makes sense since we believe the southern region is hot enough and temperature is not really a limiting factor that's going to prevent the farmers from planting earlier. We do not find much significant results in the precipitation after allowing for these heterogeneous coefficients. One estimate that's slightly counterintuitive is in the first column, the first precipitation coefficient is positive as significant. Our interpretation is that because this northeast region is a region with probably the highest level of mechanization rate, and it's more or less similar to crop production in the US Midwest. So receiving too much rainfall right before the planting time may prevent machines getting into the field. So this is something that we have found in the Midwest. So we interpret this counterintuitive results as sort of rainfall-induced delay in planting. And this table is about the growing season length. We also see some of the heterogeneity across different regions. And because our rationale is that the growing season short-run adjustment is more biophysical. So what's reflecting here is more about the different sort of the corn traits that's in different regions that's reflecting these results as their demand on water and heat are slightly different. In terms of the general magnitude, the largest warming impact on shortening growing season will be in the northeast, the northwest, and also the southwest. And for the precipitation effects, it's largest in northeast and northwest. Probably northwest is the largest, and also southwest. So let me just wrap up. So what we do in this paper is that we use micro level data in China, and we use these data to empirically examine how temperature and precipitation are going to affect growing season adjustment by changing planting days and changing growing season length. And what we found is that we find higher temperature before the normal planting time and higher precipitation is going to advance the planting date. And higher temperature and more precipitation after the planting will shorten the growing season. And those are short-run estimates. We wasn't able to find long-run estimates, but we will follow your suggestions and to do some more revision on those part of analysis and to see if we can get some long-run effects. And then for those identified short-run effects on themselves, they're statistically and economically significant and meaningful. And as I show you that at the median site under the higher emission, higher warming scenario, there could be a 20-day shift in the growing season. And based on the yield response models, we can get yield damage, avoided yield damage by more than 15% for a median site. So these results are also, we think is relevant for policy discussions. One is that we think growing season adjustments should be incorporated in sort of the policy evaluation because it matters for the cost effectiveness of adaptation policies or adaptation investment. And those investments could be related to productive investment like building infrastructures that help crops to avoid temperature, precipitation shock, and also adaptive investment, as someone mentioned, related to developing the new seeds. And from another perspective, I think this behavioral response also highlighted the value of improving weather forecast, because we think that with better weather forecast, maybe farmers are able to take more advantage of the changing pattern in temperature and precipitation so that they can adjust their growing season more actively. There are also caveats and limitations in this study. First is that what we have right now still are all short-run effects, and there could be long-run effects, and those long-run effects can be different and they're very meaningful. The other is that those identified effects in this research can be very context specific. So they can depend on the crop, they can depend on institution in a specific country. So if we turn to other crops and maybe other countries, we may see different results, and there might be different underlying stories. I think that's it. Thanks for all comments, and I'm looking for more comments and suggestions.
Great, thank you so much, Xiaomeng. That was awesome. Yeah, what we normally do at this point is if we can unmute everyone, and there's already some questions ready. So yeah, we'll start with Scott. I think you're unmuted.
Yeah, thank you, Xiaomeng. That was extremely interesting. One question I had, kind of building on your start in referencing Ortiz-Bobea and Just on adaptation, is what do you know about the genetics of corn varieties that Chinese growers were using between 1993 and 2013? In the United States, we see frequent changes in genetics and an average of about 1 to 1.5% increases in yields annually. And so, especially when you take your data and you project 1 century into the future, and I think backwards that, 1 century ago, we didn't even have hybrid corn, much less the rate of genetic change that we've had in the last 20 years. So the question is, where does genetics fit in your picture?
Yeah, I think that's a really good question. So here, I think over the period we observed, there was also some changes in terms of the seed, the trace of the seed. And one thing that I'm aware of is in China, a lot of the corn actually planted in the field may not be the seeds that farmer perceive. So there's a mix of different trace and sort of contamination of the genetics. And we don't have very good information on this, but we certainly should look into those issues. And regarding you talk about projection, I think that's I agree that when we do these sort of projections, so generally what we do is we keep everything at the current level or at the level we observe, and we assume that the only thing changed is temperature and precipitation. So in this sense, those projections don't really make much sense. So what they do is just to contextualize sort of the magnitude or how much those estimates represent the effect. But I agree that so in projecting those outcomes, we are actually not capturing those change in terms of technology, seed breedings, and also a lot of other stuff. And yeah, I think that's a fair point. And I actually don't know from an empirical perspective how we could actually improve on that regard. Yeah.
So you don't have access to data on genetic traits that were dominant by region over time in China?
We may have some official data on that, but I don't know how accurate those are. Because what I heard from people is that a lot of the seed actually transacted are not really the traits that those sellers are advocating. So there could be misalignment between the official information and the actual seeds. But for sure, I should first check available information on what we have from the official channel. Yeah.
Maiwish, you want to ask your question?
Yeah, thank you. Again, I want to add congratulations on a very nice paper and presentation of
Thanks.
yours. So maybe I missed this when you were describing your data, but I had this question on your unit of analysis, I, which is the agriculture site. How do you define that? Is it just one farmer per site? I mean, where does farmer fit into your agriculture site and this whole data? Okay,
so yeah, that's actually a very important question because it matters for how we understand those estimates. So the idea here is, it's not the idea, so the case here is that all the fields are still planted and managed by farmers. And this monitoring sites are sort of independent from those actual operations. And so those monitoring sites are determined by a protocol that those sites, the location of those sites can be representative of the agricultural production in the surrounding region. So this is something, the location of the site is determined by the monitor system, but the production activities are still done by actual farmers. So they're in some sense independent with each other. Yeah.
So they're basically on-farm trial sites in the literature that we, for agricultural research purpose, there are on-farm trial sites that are set up. Is that the concept here when you say agriculture site? Or this is different in the
I'm not sure if they're equivalent. So the key here is that I think those So those production activities are not guided by those protocols in the monitoring system. So that's
so,
the key.
So who keeps all the data record of planting date? Is there a survey done at the end of each season? How is this data collected?
So the system is gonna first determine those sites. So they determine the location of the sites, or actually the parcels, as the object they will monitor. And then during the growing season, or right before the planting time, the normal planting time, they will send expert. Well, I think the expert will go there on a 10-day basis. So every 10 days, they will go to the site. And when the production has started, during that period, the expert is going to check the condition of that parcel of land in their monitoring system every day. And every day they monitor what's going on in the field, and by observing the conditions of the crop, they determine which day, say, is the maturity date. That's how they do this.
So, okay, so thanks for clarifying that. So this is not, in a sense, like just doing a farmer survey, and this is—
No, it's not the farm survey. It's like a scientific
That's right. So it is an observe. I mean, if my plot is selected for monitoring by a Chinese government, wouldn't my behavior change? That somebody's observing every 10 days, coming to my farm and seeing what I'm doing and not doing. And in that sense, maybe your data may not be that representative of the behavioral responses of farmers for the region. And doesn't that make it question the external validity?
Yeah, I see your point. I think that's a fair point. So here we cannot fully eliminate that possibility. But in terms of the purpose of setting up this network, the purpose is really through monitoring those sites, the government or the institution affiliated with government can have an accurate sense on what's going on all over China in terms of the crop conditions, in terms of how, say, natural disasters affect crop production in a certain area. So in terms of the incentives of those monitoring people in the monitoring system, they really wish to be representative so that information collected from those sites can represent what's going on in other regions. Yeah.
Sure. Yeah, I'm not undermining the value of the data or the whole system of monitoring. It's there in many other countries also. And it serves very good purpose, sometime even for crop forecasting for the government and things. I'm just saying maybe you may need to bring that in your discussion of the results, or when you are to qualify perhaps the external validity of it. That's all.
Yeah, I agree. I think that's a very good suggestion. We should certainly do that in our description of the results. Yeah, thanks.
Thank you. Thank you.
Xiaomeng, this is Hongli here.
Yeah.
So I'm not sure whether you covered this point. It's just the intuition that the change in growing season, the potential for adaptation through growing season might be related to the current length of the growing season. Like, for example, if in a region the growing season is already very long, so maybe there's less potential, I don't know, I guess except genetic improvement to adjust than in regions that the growing season is much shorter. Like in the US, in the central corn belt areas, the growing season would be much longer than the age in the north, like in the Dakotas areas. So I'd say there's much room for adjustment in the northern part. So this pertains to my first question. I still think that as the temperature rises, the northern part, the intuition still suggests that they will, and I think it is it has been the trend that they can get a longer growing season varieties, therefore they will get a longer yield. So I'm just wondering that the assessment how growing season changes might be affected by the current growing season length.
So I guess like regarding the first point, I agree that there could be heterogeneity related to what's their original length of the growing season. And I guess the last part, when we look at regional heterogeneity in the growing season length response, we may sort of capture some of those effects. And regarding your point on when you bring forward your planting date, and potentially you can have longer growing season to plant a crop that give you higher yields. It sounds like a yield. That sounds like a seed shifting story. It's like switching to another seed that could deliver higher yields. I think there's potential for that. In reality, we probably won't be able to detect that because we don't have this sort of seed-specific information. I guess in this sense, what we are estimating in our growing season length regression is sort of the average effect. So if there's some seed changing that leads to actually longer growing season, those will be sort of masked in our average effect estimated. I guess that's how I interpret the relationship between them. But I see your point. I think there's potential for that type of change.
So, well, in a way that, I mean, by the way, I really like your presentation. It's very interesting. It's just, so I think your adaptation, it's captured through econometric estimation. So you don't really specify how and the reasons that the adaptation has taken place. So I think your estimation should capture all factors that contributed to the change. In that sense, then technology change, seed or other agriculture practices should have been reflected in your estimation. Isn't that so?
Oh, I think, I guess like my understanding is that if the technology change is induced by those changes related to planting days and growing season length, then those parts of technology change effects will be captured in my estimates.
That's right, yeah.
If there are other technology change that's unrelated to the story I was describing here, then those will be in the trends coefficients or the fixed effects that won't be captured in my weather estimates.
Yeah, yeah. That's just saying. It's just that I think for both that the planting dates and growing season may be, as you mentioned about the spatial heterogeneity. So if you look at the marginal areas, maybe the effects probably will be more pronounced. But,
yeah, we can check that in the data. Yeah, thanks.
Mywish, did you have a question?
I'm so sorry. I forgot to lower my hand. No,
no worries.
Thank you.
All right. Well, it's after 12:30 here, and it's the middle of the night where you are, Xiaomeng. So thank you again so much. Scott Swinton writes in the question and answer. Great presentation. Thank you.
Thanks.
I agree. That was really great. I always learned so much from you. So thank you.
Thank you, everyone, for coming here, and thanks for all the suggestions and comments. Thanks.